Okay, and now it is my pleasure to introduce to you Eric Blossom. Eric Blossom is the originator of the GNU Radio project, which is a real-time signal processing framework. And he will now talk to us about how you do radar with low-cost tools and free software. Welcome, Eric.
Very good, thank you. Hi everyone, it's really great to be here, and I want to do, before we kind of really dive into the radar part, I want to give at least a couple minutes on GNU Radio. I've done that kind of talk a bunch, but I'm not sure who's seen it. So GNU Radio is fundamentally a free software toolkit for building real-time signal processing systems. And generally speaking, what we use it for is doing radios. That's just because it's our personal interest, but we've got other people who are using it for radio astronomy. There's people doing like atomic force microscopes using GNU Radio as the control loop for those. It's a pretty good sized chunk of code. It's about 250,000 lines of code. It's in C++ and Python, and it's fun to play with. So kind of heading down the private investigations thought we were interested in, well, what's really flying around out there? Where are the black helicopters and are they coming? There are also people who do all kinds of different stuff with radar. So I just want to get going here and see, we'll kind of cover radar, a little overview of radar in general, and then the kind that we're building, and then we'll show you what we got working. So to start with in radar, it's been around for quite a while. It's an acronym that stands for radio detection and ranging. But in these days, it's more than where they mean ranging is distance. Really, at this point in the game, people really want to know where stuff is. And pretty much how it goes is, I don't know how it is here in Europe, but in the US, years ago, before like digital TVs came out, that you could be watching your television and an airplane would fly over and the picture would get all wiggly. And then it would get back good again. Does that, anyone have that experience? Yeah, okay, good. So anyway, we would call that like multipath, or this idea that there's like a signal coming the direct path to your television, and then it's also one is coming up and bouncing off of the airplane and then back down. So what radar is really all about is watching the stuff bouncing off of things. And the things you could be bouncing off of could be, people walking on the ground, they could be cars, they could be airplanes, they could actually be satellites. People use radar to watch where satellites are. Lots of good stuff. So, and depending on the kind of radar system you build, there's a bunch of stuff you could figure out. And you get some of these or all of these depending on what you're doing. So how far away it is. This was the real first use of radar. They basically would send a ping out and they measure how long it takes to come back. And that gets you how far away. You can also figure out how quickly it's moving towards you or away from you. This is because of the Doppler shift. Like if you're watching you're at a racetrack and you have like Formula One racing and the cars are going right on down the straightaway. You hear the engine, the pitch of the cars comes up and then descends as they go by. That's the Doppler shift. So it turns out it works with radio waves also, not just sound. Bearing, kind of the direction of the object. If you think about typical airport surveillance radar, they have a thing that spins around. So they get the bearing by kind of mechanically knowing, well, I had my antenna pointed over that way. And then some of the kind of bleeding edge stuff that is very popular in certain areas is this idea that I should be able to tell actually what kind of an object it is. And they can do things like this. There's some really fancy stuff they're doing in kind of the money is no object department here. They can kind of figure out what stuff is by watching the radar cross-section. They can watch how the radar cross-section changes over time. They do like these synthetic aperture radar where they get like a two-dimensional image, and again they're doing like fast Fourier transforms in 2 dimensions, and then they map it up against some other thing and they go, it must be such and such a kind of airplane. There's other cool stuff, just in the other cool stuff you can do with radar, is that when you look at airplanes, it turns out that, for example, if you're looking at propeller-driven airplanes, you can actually tell that it has propellers, because in fact the rotating blades show up as sidebands in the radar return signal. And same thing with jet engines, believe it or not, is that because if you have an angle where you can see the turbine spinning, you can say, oh, it must be spinning this fast or it's got this many blades. Helicopters, of course, are the same kind of a deal. So there's a bunch of kind of interesting stuff that shows up. All right, radar's been around for quite a while. Christian Helmsmeyer is the first one that I know about, spark gap transmitter, and he was detecting ships. These guys, the next people is Holt and Young. These guys were at the US Naval Lab. They were actually doing propagation experiments with HF radio into the ionosphere, and they had antennas aimed up. And all of a sudden they noticed, we're seeing like the wooden boat that's in the river over there causing a problem. They're going, oh wow, look at that. And then in the UK 1935, they actually set out and said, yes, we think can detect aircraft, and they ran an experiment and could do it. The stuff really heated up in World War II, kind of like all sides in that were building radar systems or attacking other people's radar systems, and it got, that's kind of where it really geared up. Okay, this is kind of your typical kind of radar thing you'd see at the airport. It's going to be spinning around. This is really the part that we think of as the radar. This is actually just a big reflector. It's the dish, and it's not in this image, but out here somewhere off the right-hand side is the feed horn, where they're actually transmitting the signal in and listening out. How these things work is they send a pulse out. So the transmitter runs for a little bit, and then it stops, and then it listens, and then it sends another pulse out, and then it listens. So it's basically a pulse-based radar system, and the transmitter and the receiver are at the same location. So you run one, and then you listen, and there's all this fancy stuff about how you design, what kind of signals you send, and how wide a frequency they are, and how they're modulated, and how frequently the pulses go out. I mean, you start thinking about if you send these little pulses out, there's this ambiguity. If the pulses are closer together than how far away stuff, all of a sudden you can't tell if it's far or close. This is another kind of mainstream radar. This is, in one sense, this is the PAVE pause system. This operates in a 400 megahertz band. Each of these big panels, this thing's about 100 feet tall, probably, so 30 meters probably tall. Each of these big panels has about 3,000 separate antennas with transmitters and receivers behind them, and each element is about 300 watts. This thing and basically by changing why they're called phased arrays is because changing the phase, basically timing an angle of what you send to each element, you can steer the beam around. So even though there's no mechanical moving, this actually beam, they can sweep it around. There's two of these that I know of in the US, one's on the East Coast and one's on the West Coast. This has a lot in common with the other one we just looked at, which is the transmitter and the receiver are in the same place. So this thing does the same kind of trick where it transmits, and then it waits, and then it listens, and then it goes and it transmits again. Okay, and yet here's another one. So this is your basic, radar gun or whatever. This one typically operates at about 10 gigahertz. Same basic idea, that it's a pulse-based radar system. The transmitter and the receiver are in the same place. They run the transmitter for a little bit, they listen, and they're basically measuring. In this case, they're measuring Doppler. It's like they're bouncing it off your car, and they want to know, is it coming towards them or going away from them? All right, the radar systems we just talked about, all three of those are what we call monostatic radar systems. Those are kind of the traditional ones. That's where the transmitter and the receiver are located at the same place. Another interesting class, and it's the one that we'll be using here, are called bistatic. And this is a situation where you have the transmitter and the receiver are not in the same place. They could be separated by tens of kilometers or hundreds of kilometers. They really just depends on how the system's put together. The final category, which I'm not going to talk about except just to mention it here, is the case they call multistatic. And this is a case where you have multiple transmitters, multiple receivers. They're networked together, and they kind of all figure out by watching everything together and kind of doing the sensor fusion thing about what's going on. So the bistatic case, transmitter receiver are in different places. And where this came from originally was, you know about anti-radiation missiles? These are the ones that they have on airplanes, for example, and they watch somebody turn on their little radar system on the ground, and then they just go, fire the missile and have it home in on the radar system. So that was the initial thing about maybe we should put the transmitter and the receiver in two different places. The other reason that they use this is this remote target illumination. This is more of a This is an exercise in engineering, because what you have in this situation is typically there's some aircraft flying around, like say an AWACS, that has a great big antenna on it that has the transmitter and shines down on the target on the ground. And then a missile is launched, but the missile, because it's physically very small, has a very small antenna on it, which means it doesn't have much gain. So what they get in this case is they can have this big transmitter antenna, which can send a lot of power, and a small antenna on the missile or whatever, and it all works out. I guess that's what they call it. Okay, here's the basic diagram on bistatic radar, and we'll see in a minute why we like this. So we've got this at the bottom of the screen here. We've got this visible up there. Let's see. Okay, so we got the transmitter, and we have the receiver. Now, all that we require in our case is that we know we know the relationship between the transmitter and the receiver. So we know, kind of arbitrarily, we could say, well, they're on the horizontal line, and we know how far apart they are. Then we've got this target or targets up here. And so what happens is the receiver sees two signals. It sees the direct path comes off the transmitter, like the short way. And then also there's this other path, what they're calling the illumination path over here. So it's basically the signal goes off of here, bounces off my target, and comes back here. So if you start thinking about, well, what can I do with this? If you can think about like you've had this pulse, you could measure like the leading edge of the pulse, and you would see the pulse come twice. You'd see it come once really loud, just kaboom. That's the direct path. And then you see a delayed version of it that comes sometime later. And how much later it is basically the difference in these two path lengths. So you've got the short path, L, and then you have the long path, RT plus RR. So basically, you know the speed of light, and you know this difference in time. So this starts to give you how you can begin to put the solution together. It turns out knowing just the time of arrival is between the two pulses is not actually enough to physically place the thing. Because if you start thinking about back to some analytic geometry, that describes a hyperbola. So there's a whole family of places that target could be for any given shot where it is. And it turns out that if you just take multiple collections or you throw in also information about its velocity, you can start figuring out actually where it really is. The other thing to notice is we will talk about the distance, where within the monostatic radar case, since the transmitter and the receiver are in the same place, you send this pulse, it goes out, hits the target, and comes back in. And if you just measured that time of transition, that's really like it goes out and back, so it's twice the distance, and you know the path out is the same length as the path back. In the bistatic case, they're potentially different lengths. So you get this idea of distance, but it's not just one way. Likewise, when you look at the Doppler shift that you get in a situation like this, it's the change, you know, normally this Doppler, you think about it's the change in the path length. Well, in fact, it's still caused by the rate of change of the total path length. But again, you don't know if like the RT path is shortening or lengthening or the RR path is shortening or lengthening. So it's a little more complicated math than in the monostatic case. The other thing, kind of one of the basic rules of thumb is if you're working your math here, and if you shrink that baseline L down to 0, it all ought to work out just like the monostatic case, where they're both in the same place. And if they're not, then you're, you know, oops, you don't have it right. Questions so far? All right, and then to make things more interesting, in the general case, everything is moving. So you got the transmitter's moving, and the receiver may be moving, and the target may be moving. Again, all we require in this is we need to just know the relationship between the transmitter and the receiver. Examples where the transmitter and receiver are moving would be, for example, two aircraft, one of which is illuminating, one of which is watching. It could be the transmitter is a satellite and the receiver is an airplane. The target could be also moving. So what happens is kind of a sort of a footnote is they have this idea. People here have been on boats with radar systems, and they have this like sea clutter where you get like the waves start showing up and you can turn the knob down. Well, you can start messing with the clutter, like what stuff is reflected to you that's off of the ground by varying basically the velocity vectors for the transmitter and receiver, since you control those. So there's some cool stuff that kind of comes out in the fancy case. All right, no radar talk is complete without the radar equation. So basically, the thing on the left is how much power is reflected back. And then the P sub T is how much power is being transmitted. And then that big G is kind of the gain of my transmitter antenna. It's how, basically how big or directional it is. That A sub R is really the corresponding answer for the receive antenna. They just draw it a different way. Sigma is what they call the radar cross-section of the target. So a bigger, and it's got units of square meters. So the bigger the target it is, the more power gets reflected back, which makes sense. You got a huge object, easier to see, 757 than to see some little Cessna or something. And then those are the two path lengths. Where this comes into play is you're trying to figure out how good the RF performance, the radio performance needs to be, and kind of how does this perform in a noisy environment. And also, since the farther away everything is, you get this like 1 over R squared basically loss. So the return signal falls off pretty badly. Okay, so now passive radar is the one we're interested in, and it's a subclass of bistatic radar. So the math turns out to work out pretty much the same way, except in this case, we don't own the transmitter. So we're going to use somebody else's transmitter. And this has got all kinds of great advantages. The starting with which is we don't have to run the transmitter, we don't have to pay for the transmitter. You look at radar transmitters, often they're like running at a megawatt. They require, very fancy, hard to get license. I'm certainly not going to pay the power bill on the megawatt transmitter, or, excuse me, I need this big chunk of land, and, don't walk near me when I'm blasting away here. So we look at, it's pretty interesting. You look at, there are some passive radar systems. There's one at the Haystack Observatory at MIT, and they have this giant dish. They got 2 of them, actually, one of which just points straight up. It's not steerable, just points straight up. And then they got one that steers. But they use it for doing, mostly they're looking at stuff in the ionosphere. It runs at about 400 megahertz. And they also have observed that they see all the low Earth orbiting satellites. It's like, okay, good. So we look at all right, transmitters, what do we got? All right, we can get, there's a bunch, all right. That's kind of like there's cellular up there, there's public safety, there's microwave point-to-point. It turns out there's actually no FM transmitters up there, no broadcast FM. That's a megawatt television transmitter. There's another on the order of megawatt television transmitter. They're all over the place, okay? So the question is, okay, well, whose are we going to use? So we find somebody's transmitter. Then we need to either have multiple coherent receivers. And what we mean by coherent is that, because we're listening to two signals. We might have one antenna is pointed directly at the transmitter, and maybe another one is pointed sort of away from the transmitter, or maybe we're building this phased array where we have a bunch of antennas. The trick is that we need to be able to do, when we're doing sampling, and when we're doing the down conversion of the RF signal to baseband, where we're going to sample it, all that needs to be in lockstep. So there's this tricky thing about, if you took two radios, mostly radios don't come where they can all be exactly synchronized. So this is kind of a piece of the problem. So, watch the reflections, do the math, and figure out where it is. How hard could it be? Okay. Don't you love the problems that have? This is one of those problems that a real simple description. Okay, so we say, all right, well, what are we going to use? And again, the thing is, we don't control the signal out of the transmitter. So we don't get to say what they're transmitting in the traditional radar system. The guy on the receive end knows exactly what the transmitter is transmitting. They either know kind of a priori, like they know if it's a spread spectrum transmitter, they know exactly the spreading code they're using. But in our case, we can know just because we know the class of signals it's transmitting. We have some information about it. So broadcast FM, this is about 100 kilohertz wide. It's probably the easiest one to do. Analog or digital TV. This is actually probably the more interesting one as far as the kind of how fine of resolution you can get, and we'll talk about that in a little bit. And then there's an outfit in the UK called Roke Manor who claims to be doing GSM-based, they're calling it CELDAR, where they use GSM base stations as the transmitters, and they watch the reflections. From my reading of their literature and talking to some other people, we're not really clear how useful it is, because the base stations are relatively low power. So you don't see anything until it's right on top of you. So that's kind of like, unless they're looking at vehicle traffic or something like that. But aircraft, they're on your head before you notice them. I don't know of anybody who's actually done UMTS, but it has the advantage of being quite wide bandwidth, which allows you to do a more precise fix on the location. Other choices, actually, these have all been tried too. High-powered satellites, the DBS. I know that people have tried this with military satellites, which aren't this high a power. So this might work. I know of people who have done it and made it work with GPS satellites. And so they have the satellite as the transmitter. And then they're flying an airplane as the receiver, and they tell me they're watching, weather or waves on the ocean. I think they're looking for ships. But again, the cool thing about the GPS stuff, the satellites aren't that powerful, but they do cover everything. And it's a spread spectrum thing, so you have this big coding gain. So you can basically correlate stuff and go find the weak reflections. And then another trick that's been done really all the way back to World War II was you take advantage of other people's radar transmitters. Sometimes they're a friendly transmitter, and they could be a hostile transmitter in kind of a military situation. But again, they're high-powered, they're transmitting, and as long as you can point at them and you can get to see the reflections back, you get to take advantage of that. The secondary surveillance radar system, this is like the squawk ID that, like the air traffic control, they like to know just not where it is, but they like to know like altitude reporting and all this. So there's a secondary thing that pulses out at the airplane, and when it sees it, it has its own transmitter that sends some encoded information. That stuff's about 1.9 gigahertz. Okay, so before we headed down this path, we said, are we totally crazy, or has anybody else done this? So the top one here, the Lockheed Silent Sentry, is in the money is no object, let's make it work. It was based on doing taking advantage of broadcast FM stations. One thing that people, to kind of back up for a second, what they like about FM is that the signals they're all over the place, they're all around the world, and they're fairly high power, so it's not uncommon that they're 30 kilowatts. And because of the frequency range, they actually have good propagation characteristics. So you can see things in the conventional case, you get line of sight to the horizon. So depending on how high up you are interested, you can see a long way, hundreds of kilometers. And then the second one I'll talk about in just a minute is this Monostache Ridge radar. That's the total low-cost system that is really kind of inspiring, but they take advantage of a relatively unique feature that the rest of us don't have. So here's the Lockheed Silent Sentry. They sell this thing for on the order of $1 million. You know you're in trouble when this rack to the left is full of all this very expensive HP test equipment over here. This thing fits, they've got a fixed installation, they have a mobile installation. The mobile installation kind of comes in a container, and then it has these, their phased array antennas down the side of the container. So I think they use the container body itself as actually the screen behind it, and then they've got the antennas vertically, dipoles across it. So we figure, well, hey, let's see what we can do. If they do it for $1 million, can we get it for 1,000th of that, say? This system was the one that was really the most inspirational to me, because these guys at University of Washington, they did something very simple. I mean, they scored major points in the hacking universe, is that the university is located in Seattle, but the university also has an astronomical observatory about 150 kilometers away, but there's this mountain range between the university and the astronomical observatory. So what they do is they have one antenna that's just hanging out the window of the EE department, and it sees the transmitter that's right over there, the rock and roll radio station, FM station. Again, it's about 100 megahertz. And then they have another antenna. This is a YAGI, directional antenna at the observatory that's pointed north. What they're interested in is ionospheric phenomenon. They really want to know about plasma, aurora borealis, this kind of stuff. There are people who really care about this stuff, and these are some of them. I mean, it's cool. They get their own journals. Let me tell you, you're going to go, oh wow, there we go. And the cool part for them is that thing about how you get that coherent. You got to have that coherent sampling on both places. Is they use GPS clocks on both ends. Now, one thing I don't know that people know about GPS. Mostly we think of it as for location. But you can buy receivers that are specially tweaked up to do really good timing. So they get really good. I mean, actually there's a mailing list called Time Nuts. I don't know if you guys are familiar with this. These are for people who they have the hydrogen maser in their basement. I mean, they're out of control. But if you want to know what time it is to 1 part in 10 to the 12th, there are people out there who will tell you. So they know, they got their own little eBay, the cult of eBay, where they get the rubidiums and the cesiums. Those things are relatively affordable. The hydrogen maser, I guess that's really the holy grail. When you've got that, you're as good as National Standards Lab. So again, the cool thing they do on this is they got this mountain range. So this avoids the problem of how do you keep the direct path from just swamping this little tiny reflection that comes back. The other thing is, so they've got their antenna aimed up at a pretty good angle, because again, they're in Seattle and they're looking north up over Canada towards Alaska. And they see stuff moving that's 1,200 kilometers away. That's like the edge of the atmosphere slanted up. And it's pretty cool, because I've seen some of their presentations and some of the graphics they've provided, and they've got big stuff moving, say, 1,500 meters a second up there. And if you're HF amateur radio operators, basically the stuff they're mapping is the source of sporadic E propagation. So, all right. So then it comes down to, all right, what are we going to do? We want to build, a radar system. We're certainly not going to run the transmitter. That's, we just punt on that. And so we picked FM broadcast. Again, the main choice is there's a couple of existence proofs that it works, and the other thing is that with the hardware that we already have, we think we have a pretty good fit on what we can do. So the signal's about 100 megahertz. This is 3 meter wavelength. Kind of gets into why you care about stuff like that is it sizes your antennas. So there's some stuff we'll be doing later. And one of them is to build this big screen between our antennas. But you start looking at these big metal screens, and they've got to be 1.5 times their wavelength. So all of a sudden I'm thinking I have a 5 meter by 5 meter big square of mesh, and it starts to not look very portable. So, okay, there's the theoretical distance resolution you get basically is the speed of light divided by the bandwidth of interest. That gives you about 3 kilometers here. So you can kind of think about this. You're getting how do I want to say that? Anyway, trust me, that's about the answer. There's also this other technique you can Google, follow the tips in the previous talk. On super resolution techniques, there's some great academic papers on this, and this stuff's getting applied now. All right, now back to the reality of why we picked this. We need to sample these multiple antennas coherently. In the strategy we were going to do, we're going to say, okay, what's the simplest thing that could possibly work? And that's 2 antennas, one pointed directly at the transmitter and one pointed away. So in the simplest case, we got to be able to sample 2 things at the same time, and have we care about is it one sample behind or not, or what's the phase of it. So some of you may have seen these things we've had here. This is the, I got a picture of this in a minute, but I just wanted to show you this. Instead of having that rack of gear, we're going to try to do it with this thing. This is the Universal Software Radio Peripheral. And the hardware was designed by Matt Edis, who's a colleague of mine, and then this whole design is open source, and all the software is in the GNU Radio code base. So what it has is 4 A to D converters, high speed, 64 megasamples, and 4 D to A's for transmitting, FPGA, all that. Looks like that. The cool thing about this is we can do up to 4 channels. And if you look, this is about, by the time you get all the pieces you want, it's about $700 US. And the cool thing is there's nothing else out there that comes anywhere close to the performance this thing has for the price. I mean, there's lots of people that'll sell you 4-channel high-speed stuff, but they're going to be like $10,000 or more. It's sort of the same block diagram here. There's these receive daughter boards, the converters, FPGA in the middle for, we do some of the signal processing on the FPGA, basically do channel selection and filtering on there. And it hooks up over the USB 2. Everything in the system is downloadable over the USB. So we load the firmware into the USB 2 controller over it, and then we use that firmware to load the contents of the FPGA. So it's completely flexible. Okay, and I wanted to talk a minute about this bandpass sampling. Not like we're going to do all the math here, but just to give you folks an idea about this if you haven't heard of this. The idea generally is that if I want to sample an analog signal, I want to make sure that I'm not losing any of the part I'm interested in. And this guy named Nyquist, a while back, figured out that you needed to be sampling at least twice as fast as the bandwidth of interest. So in the cases, like people mostly come out of engineering school, the first time they look at this, they're always thinking of the low pass case, where that means if I have a signal that's 100 megahertz, then I must need to sample it at like 200 megahertz or 250 megahertz. Well, if I were trying to capture everything from 100 megahertz and down, that's true. But if I'm only trying to capture some stuff that's like centered at 100 megahertz, but maybe is a few megahertz wide, then I don't need to run that fast. So the trick is that at this sampling rate over 2, there's aliasing that occurs. So it's actually like chunks of the spectrum just fold back in from both sides. So you can figure out where that's going to happen. And the cool part is that, for example, our analog to digital converters have a very fast front end on them, which actually we can run them, we can put signals in that are up to 400 megahertz, even though we're only sampling in 64 megasamples, and we get reasonable results. So what this is good for in our case is it means that we don't need any, so for sort of regular radio guys, there's no analog mixer in the system. There's no like superhet anything. So basically no analog mixer, no analog oscillator, which basically gets rid of that whole problem, because otherwise you have to figure out how to make that coherent also. So the beauty of this from our point of view is we get the coherency, and all we have to control is the sample clock on the analog to digital converter. Okay, so we went and we said, all right, what's the simplest thing that could possibly work? And this was the two-directional antennas, point one at the transmitter, one was about 120 degrees away. This was because it was towards the airport. 2 low noise amplifiers, and then one of these USRPs. Okay, it looks like this was the setup. These are, you can kind of see there's 2 of these directional antennas. These were actually, we get them at Radio Shack in the US. They're for FM radio, and they're very inexpensive. They're like $25. By the time you get the mast and the stand and the cable, you probably got about $100 in each one. And then there's, you can see the other one in the other direction over there. The transmitter in question is on that mountain right there. There's a whole bunch of them over there, but that's where we're pointing the one at, and it's a clear line of sight. And then here is the sort of, in the field, so basically it's, laptop, it's duct tape, it's some cables, and the USRP is in the cardboard box under the table there. So we sit outside, we got this all set up, we're in the middle of the desert, and we say, okay, anybody see any airplanes yet? Okay, the first time out, we want to make sure that we have a prayer this thing's going to work. So we look and we say, okay, good, 737, westbound, and you log the time and say, start recording data, and the files are all time-stamped. So we're basically collecting data from 2 channels and writing it to the disk. So we collect, an afternoon's worth of data. Then we go, okay, so now let's run our untested analysis software, and let's plot up and see if we can see this range versus Doppler. So this is the idea, how the frequency shift of the thing and how far away it is. So we go, hey, all right, look at this graph. So the y-axis is Doppler. So this has lots of bins in it. So the way this was plotted up is there's like 256 possible frequency offsets that it could be at. And this is about 30 pixels wide here, 30 bins wide this way, which is about out to 30 kilometers. So, I was looking, the airplanes were closer than 30 kilometers. I figured they ought to be in there. Well, I don't know about you, but I don't see any airplanes in there. So we're going, okay, we got all this great idea, now what? So, we're big fans of let's just try it and see if it works. So then the question is, what's not working? Is it the hardware? Is it the software? On the GNU radio list, I'm notorious for saying, we need unit tests. Don't submit code without QA code. Well, okay, I'm going, okay, good idea. Maybe I should apply it onto my code too. So we had some questions, like on the analog section, do we have the proper filtering? In fact, if you look, I don't know if I actually didn't show the block diagram, but in that simplest thing that could possibly work, we left out this piece called the bandpass filtering. It turns out for doing regular FM reception, it works. But part of the problem is that really, since everything is getting folded in here with no selectivity, you got all these potentially big signals on top of it. So it works okay for the big FM stations because they really still get bounced, but I think what's happening is that the small reflections off the airplanes are getting swamped out. There's a question about antennas. Do we really have the right setup? Or the other question is the software working? So we go, aha, let's simulate first. So of course, the people I know who do this for a living, they said, you should simulate this. I'm like, okay. So now we get out our GNU radio toolbox. We have an FM transmitter in there. We got all kinds of stuff, but we got narrowband FM or wideband FM. So we say, okay, I got a random audio signal. I'm putting it into my transmitter, and instead of putting it on the air, I just put it into the disk. And then I say, okay, now we want to simulate radar reflections. Okay, how do you do that? Okay, so you got the geometry. You got where's the transmitter, where's the receiver, how many targets do I have flying around? You know, you got some geometry. You basically, so you're simulating, you know, the aircraft's flying this way at a particular altitude or whatever. And then you got to figure out the propagation delay that should be seen and the Doppler shift. So then we said, okay, let's try this analysis software on the reference signal, which was the simulated FM signal, and then basically you feed the analysis software the reference, which is basically the direct path, and then you send it the reflected stuff. So, hey, I see simulated airplanes. Okay. So this is actually great news, let me tell you. It meant that the first software didn't work. Now, I think there's also probably some other things to fix yet. But so what we're looking at here is two fuzzy dots on a black background. But so the horizontal axis is the slant range. It's distance. So that's about 100 kilometers from the left to the right. And the y-axis basically has a 0 in the middle. Clearly, we need a little, like, you know, tick marks on here. But anyway, zero velocity is in the middle. And kind of at the limits of plus and minus on there, it's about, maxes out about 750 meters per second. So that's kind of the speed of a commercial airliner at cruise. So what we see are these two fuzzy things. Turns out there's lots of stuff you can do to tighten them up. If you start thinking about how let me back up for just a second. So remember I was talking at the very beginning of the talk about how they had these radar systems where they sent out a pulse and then they stop transmitting and then they listen? Well, we don't control the transmitter, so it's on all the time. So the trick we get is that we can listen for a long time. And it turns out that the broadcast FM signal, particularly if it's turned to something like, you know, very raucous rock and roll, it's got really good properties for us. If they're just talking, it's not so good, seriously. But if they're really cranking it up, you have this idea that when how you figure out where, you know, you're trying to make this time measurement, what you're actually doing is you're correlating, you're sliding kind of a delayed version of the signal against a non-delayed version of the signal, and it's brute force. You say, okay, try matching them up here, and you basically compute this. It's the correlation, but it's basically you take complex conjugate and sum them. You know, and you can pick how big a window you like, and the bigger this window gets, the tighter you fit. So since I can do a second's worth of data, it's like 250,000 samples. These ones were done with 25,000 samples here. Anyway, so you get knobs to twist on, you know, how does it look. Okay, so let me show you this thing animated. So again, the other thing to remember is that this isn't like X and Y position in this thing. This is like the raw return that we get out of sort of the first cut of the analysis. So this is how far away, basically the distance in here is the difference in the direct path distance and the full reflected path distance. And then the Doppler, the Y component, is the rate of change with regard to time of that distance. So, hold on. So here are these two airplanes, and now we're going to see them actually moving around. And this is actually like 4 minutes worth of data. This is like really 4 minutes worth of data that's running. We're sampling it every 5 seconds, and we're playing it back 10 times fast. So if you look at the one that started on the right, it kind of loops around and comes back. And the other one kind of came in and goes thing. So let me do it again just so you see what happens here. So the thing to know is I used 16 kilohertz wide Gaussian noise. Yeah. But I've also tried it with real FM signals I recorded off of the air, and that works too. We could throw FM. We could have like the selection of which is our favorite radio station, you know. So we could do that. The GNU radio transmitter, you just plug whatever data you want into it, and we can, you know, resample up or down to whatever rate you like. So anyway, the thing to note is that in reality, both of these simulated airplanes are flying a straight path. They're constant velocity, you know, headed one direction. But we see them, they appear to be bending. And again, the one to the left is coming very close to where we are, because basically, see how the distance between the reflected path basically goes to 0 right there. It kind of flies right over us. And this one out here is flying horizontally, but north of us. So now what we know is that we have a clue about extracting data. This is good. So then we said, aha, let's take the old data we collected, the afternoon's worth, and run it through this and see if we see anything. Well, it's not good. So we got other problems to fix. But we really do fundamentally think we're going to get there with this. We think this is a pretty good step. There's more to do, kind of the next piece of this. Meanwhile, so kind of where we go from here. So now we know we have software that we have a clue about. We should be able to use this simulated model to really go back and figure out how good does our analog hardware need to be, and what is it likely we should be able to see. I mean, as a friend of mine who I was talking to about this described, he said, you're gonna start with the airplanes that are casting shadows on your house, right? And I said, yes. So we have like, you know, I live in Reno, Nevada. The airport is relatively close. The airplanes fly pretty much over the top of the house. We should be able to see those things. They're big. It's not like we're trying to find little tiny things. My friends who are real RF experts, they keep telling me, you need helical filters. I'm like, okay. I'm looking for people who want to build helical filters. Those are actually a very cool mechanical engineering hack. They like to do them at 100 megahertz. They end up being about, they're like 10 centimeters by cylinder, 10 centimeters across and 5 centimeters tall. And there's like a little, so it's like a piece of copper pipe that then has like copper helix inside of it that's only got one end connected, the other end's freestanding, and it works because of the mechanics that are right inside of the thing. So those are very low loss, meaning that we don't, basically we select just the part we want and our signal isn't attenuated. So we might try some other things too, but that's, the people who are in the know keep telling me this is the answer. And I haven't found them. You can find them off the shelf at about 400 megahertz. They use them in lots of radios, but apparently they're not, I haven't found a supplier that just sells them to you. Other ideas on antennas. So we looked at, and again, this is from looking at some of the literature, what did other people make work? See, part of the problem may be that we're getting swamped out by the main path transmitter. You start thinking about this. This reflection off the airplane could be, you know, minimum 100 times smaller, you know, 20 dB down from the main path. So you think about it, you got like this spherical wave that's propagating out and it hits something and then it propagates back to you. So it's small. So one of the tricks that people have used is they need some way to keep the main transmitter from just really hammering them. So the guys at the University of Washington, they had this clever thing, you know, relatively unique to them, is they put the mountain range between the two, solve their problem. The other people put this big metal screen behind it, and it's a classic setup for, like in electromagnetic labs, there's like a canonical antenna they use for measuring field strength, and it's got that shape. So it's a big grid with two dipoles in front of it. The other thing are antennas called corner reflectors, and basically they're a quarter wave dipole. So again, that's a quarter wave of 3 is a nice smaller thing. And it's basically a big triangle, like this with a metal plate on the bottom. Those should work pretty good too. So that's the immediate short term. Then what gets interesting is, so we get the raw radar return, and we've got sort of, it's kind of like you think about you're doing your first order feature extraction. Then the other juicy part comes in here about, okay, well, it's nice to be able to determine where they're coming from. What is the angle of arrival? So then we start using, since we can do 4 antennas with current hardware, we can at least do, say, the 2 dipoles and then the reference. and we can start doing interferometry. So you have the two dipole antennas, they're half a wavelength apart, so they're a meter and a half apart. And at that point, and since you put the screen back towards the transmitter, it turns out you can only see, about half of the universe in front of you. You can't see behind you, but, that's just kind of the reality of it in this setup. So we'll do that. There's also, you may have seen pictures, there's a particular phased array antenna. I mean, phased arrays, like you see these antennas in a line a lot of times. You can also put them in a square. So there's like just 4 of them. The degenerate cases, there's 4. So it's just 1, 2, 3, 4 in a box. And we can also do that one. What's cool about those is you can steer, again, just using even 4 of them, you can steer the beam, or you can steer a null. So you can either steer like focus over here, or you can steer this part that's notched out. So maybe what we want to try is steering the notch towards the main transmitter. But the theory only gives us about a 10 dB attenuation towards the transmitter, so we may need to use both the combination of the, the big screen behind it and then the phased array antenna. There's a couple other ways we could go doing some more analog tricks, but we're going to try to do it without getting crazy about that. So the other thing that you start looking at is this idea. So I got all this raw returns, and right now we just showed you 2 of them. But the real world is really messy. So you got echoes coming back off of the mountains, and you've got you just got noise sometimes. And the trick is to figure out, what do I care about? So there's a bunch of different algorithms. People have been at this radar processing really for a long time. And one of the ways it's pretty easy is if you just start by only looking at stuff that has like a non-zero Doppler. The stuff that's not moving, probably I'm not interested in. Since I know that the transmitter's not moving and the receiver's not moving, the target's not moving, I don't know. So we get rid of those. And then the trick is, okay, now let's go, and we got all these data that we feed into this thing where we know that really there's solutions. The solution of this particular set is a hyperbola. And then what happens is, over time, they do this technique called Kalman filtering, where it's basically you have this noise, you have a basically rough guess, and then time ticks, and you go look again later. Now, the cool part, is that the airplanes we're looking at probably can't do like light speed jumps. So Newton probably still rules. So you start looking at, okay, I've got a possible fix here that's like anywhere on this branch of this hyperbola. And then 10 seconds later, I got another possible fix. But some of those solutions are not physically possible, that the airplane could not have gotten from where it went to where it was. So you start narrowing down like that. And then it gets real tricky when you got bunches of targets flying around. Also where we're going is, of course, we want this to really look like the radar screen. We'll probably even make it sweep, even though this doesn't sweep. I mean, that's kind of the artifact of back to where the thing is spinning around. They call this staring. So this thing just looks all the time. Look, 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 look. And there's a question of how often you refresh the thing is kind of like how long a period are you integrating over to get the data you're looking for. And then when this is all working, and we'll have the white paper out that says, order this thing, and then you build this antenna, and then you run this free software. Then the next thing we do is we go probably do it all over again with digital TV signals. So the cool thing about digital TV signals, because of their bandwidth, we should be able to get fixes that are within like 50 meters. So if you remember back to the FM, we get 3 kilometers, which is like, it's okay. I'm not arguing it. It's like better than 0, right? But 50 meters is very exciting. And okay, all this code is in the GNU Radio CVS. So if you can't find it, send me email. It's in there under the GR-radar module. And we have a mailing list that stuff all gets discussed on. Most of the action around the GNU Radio project is really on the mailing list and in the CVS repository. So, and then questions. We got a few minutes here for questions. All right. Yeah. This is like my main priority right now. There were some things that got in the way, like making all this data stuff work, but now that's been put to bay. So, I don't know, a couple, 3 months maybe, something like that. We could, basically we should now be able to, now that we know the software is not completely broken, we ought to be able to do some experiments on the RF side and see what we get. I mean, once we start getting the raw returns back and we can see something, then of course there's all this multiple target tracking, but I'm looking forward to seeing real returns from, you know, the hardware we got. So.
Sorry?
All right.
Sorry?
Yes, go ahead.
Right here. So this will only give you the primary echoes, right? So in order to actually use it for identifying the objects that are around, have you thought of any ways of combining it with, I mean, you obviously can't query the transponder on these planes, so have you wondered about combining it maybe with an ACARS receiver or something like that?
Absolutely, yeah. I think that's possible. We get the primary response, and then we also, you know where we know when they're being illuminated and all that. So.
Yeah, right.
Yeah, good. All right, thank you very much.